Hello everyone. Let us continue our section 11 on direct products and finitely generated abelian groups. In the previous class, we have seen that when we take the Cartesian product of n groups, that is G1, G2, etc., Gn, which we can denote it with I is equal to 1 to n Gi, this forms a group under the binary operation defined by a1, a2, etc. an and b1, b2, etc. bn is equal to a1, b1, a2, b2, etc. an, bn. So under this binary operation, you can see that product Gi forms a group. Now in the previous class itself, we have seen that when we have a member a1, a2, etc. an in product Gi, and if we know the order of each of the elements ai, then it is possible to find the order of the element a1, a2, etc. an. And the theorem says that even if a1, a2, etc. an is an element of product Gi, and if ai is of order Ri, then the order of the element a1, a2, etc. an is the least common multiple of all the Ri. So let us see an example. That is, let us find the order of an element 8, 4, 10 in the group Z12 cross Z60 cross Z12, 24. So here you can see that 8 is a member of Z12 and 4 is a member of Z60 and 10 is a member of Z24. Now we know that the order of an element k in Zn is actually n divided by the GCD of k and n. Therefore, order of the element 8 in Z12 is 12 divided by GCD of 8 and 12, and order of the elements 4 in Z60 is 60 divided by GCD of 4 and 60, and order of the element 10 in Z24 is 24 divided by GCD of 10 and 24. Now if you calculate the answers, you can see that this forms 12 divided by the greatest common divisor of 8 and 12 is 4. So it is 12 by 4, that is equal to 3. And order of 4 in Z60 is 60 divided by GCD of 4 and 60, which is 4. So you will get it as 15. And the GCD of 10 and 24 is 2. So this becomes 24 by 2, that is 12. So by this theorem, the order of the elements 8, 4, 10 in Z12 cross Z60 cross Z24 is equal to, it is the LCM of, that is LCM of least common multiple of 3, 15 and 12. We can see that it is equal to 60. In the textbook you can see that the problem has a solution given by 60 as the order of the element 8, 4, 10 in Z12 cross Z60 cross Z24. Next, let us see a definition of the subgroup generated by a collection of elements in the group. So let G be a group and let AI be a collection of elements in G. The smallest subgroup of G containing that collection is the subgroup generated by the collection AI. And if this subgroup is all of G, we say that this collection generates G, and we call AI are the generators of G. If there is a finite set that generates the group G, then we say that G is finitely generated. Now let us see an example. Consider the clean for group V is equal to EABC, and if you consider a subset AB, then the smallest subgroup containing the collection AB is the full group V is equal to EABC. So we can see that this subset AB generates the clean for group V is equal to EABC. Similarly, you can see that the collection AC, BC and ABC can generate the full group V is equal to EABC. Since there is a finite subset that generates the full group, you can say that this clean for group is finitely generated. Now consider another example. Here you can see that the group Z cross Z2 is generated by the elements 1, 0 and 0, 1. For we can see that arbitrary element in Z cross Z2 is of the form nk, where n can be any integer and k is a member of Z2 that can be 0 or 1. Now if you consider the combination of the elements 1, 0 and 0, 1 generated by n times 1, 0 plus k times 0, 1, then you can say that you can obtain the element nk. Thus any element in Z cross Z2 can be generated using the elements 1, 0 and 0, 1. So we can say that 1, 0 and 0, 1 generates the group Z cross Z2, and we can see that Z cross Z2 is finitely generated. In general, we can see that the direct product of n cyclic groups, each of which is either Z or Zm for some positive integers m, is generated by the n tuples 1, 0, 0, 0, etc. 0, 0, 1, 0, etc. 0, 0, 0, 1, etc. 0, etc. 0, 0, 0, etc. 0, 1. Now this takes us to a new theorem on the structure of finitely generated abelian groups. So the theorem number 11.12 says that every finitely generated abelian group G is isomorphic to a direct product of cyclic groups in the form Z suffix p1 raised to r1 cross Z suffix p2 raised to r2 cross etc. Z suffix pn raised to rn into Z cross etc. cross Z. Here all these PAs are primes, that is P1, P2, etc. Pn are primes, not necessarily distinct, and all the Ris, that is R1, R2, etc. Rn are positive integers. Now this direct product is unique except for possible rearrangement of the factors. Here you can see that there are two types of factors, that is factors of the form Z and factors of the form Z Pa raised to Ri. So the total number of factors of the form Z, which we call as the Betti number. So Betti number is the total number of factors of the form Z, so that must be unique, and also the factors of the form Z Pa raised to Ri, that also must be unique. Here let us see a problem. Here we need to find all abelian groups up to isomorphism of order 360. So first we need to find the factors of 360. That is, we can write 360 as 2 into 2 into 2 into 3 into 3 into 5. So we write 360 is equal to 2 cube into 3 square into 5. Now except for possible rearrangement of the factors, we can write 2 cube as 2 cube or 2 into 2 square or 2 into 2 into 2. Similarly, we can write 3 square as either 3 square or 3 into 3, and 5 raised to 1 has only one form of representation, which we write it as 5 raised to 1. Now finding the different combinations to make it 360, we can either combine 2 cube with 3 square and then with 5 raised to 1, or 2 cube with 3 into 3 or 5 raised to 1. Similarly, you can combine 2 into 2 square with 3 square and 5 raised to 1, or 2 into 2 square with 3 into 3 and 5 raised to 1. Also 2 into 2 into 2 with 3 square and 5 raised to 1 gives you 360. Also 2 into 2 into 2 into 3 into 3 into 5 gives you 360. Now using this, it is possible to list all the abelian groups of order 360 up to isomorphism. If you check, you can see that all possible combinations of the factors of 360, 2 cube, 3 square and 5 raised to 1 except for possible rearrangement are included here. Thus we have 8 abelian groups of order 360, and this is the answer given in your textbook, and you can check that. You are also requested to find all abelian groups of order 24 as a homework. Thank you.